Welcome back to the lecture series on state space modeling. We are in lecture number 6, and in the first 4 lectures we understood how to model the electrical and mechanical systems. And then in the 5th lecture we understood that if I have a state space model, I can transform that state space model into a transfer function model, and systematically we got the expression for the transfer function of the system in terms of the matrices of the state space model A, B, C and D. Okay, so G of S is equal to C into the inverse of Si minus A into B plus D. Okay, so we derived it. And also we observed certain things. That is, for an SISO system, this G of S is a straight away will give you the transfer function between the output variable and the input variable. And for a MIMO system, it is going to be a matrix of the size M cross R, where M is the number of outputs and R is the number of inputs. And also we understood that the eigenvalues of the state matrix are nothing but the poles of the system. So I can get the poles of the system directly from the state space model. That is, if I know the matrix A, I can straight away get the poles of the system. Okay, so that is what we learned in lecture number 5. So what we are going to do in this lecture? Okay, so in this lecture, we are going to work out some numerical problems. These numerical problems will focus on whatever we learned in lecture number 5. Okay, that is the previous lecture. So we'll just obtain the transfer function of an SISO system. We'll take up an SISO system and get its transfer function. And also we'll find out the transfer matrix of an MIMO system from its state space model. And we will also illustrate that the eigenvalues of a state matrix are the same as the poles of the system. Okay, and in this process also we will learn how to get the state space model if the differential equation alone is available. That is, you do not have any idea about the system. Okay, you do not have any idea about the system, but you have only the differential equation. You do not know whether the differential equation represents a mechanical system or an electrical system or an electromechanical system, nothing, but you are provided only with the differential equation. In that case, how to get the state space model. Okay, so these are the objectives. So it's going to be a mere numerical problems session. So we are taking 3 problems. The first example is on SISO system. Okay, single input, single output system. So this is a state space model given. For this state space model, we are going to get the transfer function of the system. Okay. So obviously this is a single input, single output system. So the matrices will separate. This is the state matrix A, and this is the output matrix B, and this is the input, sorry, this is the input matrix B, and this is the output matrix C. So there is no D matrix, so I can take the D matrix as 0. Okay. So we know that the transfer function of the system is given by this expression C into inverse of Si minus A into B plus D. Since B is 0, since it is a null matrix, so the equation or the expression reduces to this term. Okay. So to find out G of S, the first thing you need to do is find out the inverse of this. To find out the inverse of this matrix, first you should find out Si minus A. Si minus A. S is a Laplace variable or a complex variable, and this is an identity matrix. See, the identity size of the identity matrix depends on the size of this matrix A. Since the A matrix here is of the order 3 cross 3, I am taking an identity matrix of the order 3 cross 3. If the state matrix is of the order 2 cross 2, you should take the identity matrix also of the size 2 cross 2. Okay, so the size of this identity matrix will be decided by the size of the state matrix. So I just wrote Si minus A here. So if I simplify, I can multiply this identity matrix by S. So I'll get all the diagonal elements as S. Okay, so therefore S minus minus 2 will be S plus 2. And this is 0 anyhow. Even if you multiply by 0, yes, you'll get a 0. 0 minus 1 is minus 1. And here it is 0 minus 0 is 0. 0 minus 0 is 0. This is S. If when I multiply this matrix by S, this will become S. S minus minus 3 will be S plus 3. 0 minus 1 will be minus 1. Similarly, you can get the last row also. So I got Si minus A. Okay. So once I get this Si minus A, I need to get the inverse of Si minus A. So I already taught you, or already you know, that inverse of any matrix is adjoint of that matrix divided by the determinant of that matrix. Okay. So how do you find out the adjoint of this matrix? So you need to find out the inverse, you need to find out the adjoint and the determinant of Si minus A. Adjoint is the transpose of the cofactor matrix. I'm not going to explain you how you should find out the adjoint of any matrix. You can refer any mathematics book, basic mathematics books, which talks about something about the matrices. You can find there. Just refer some math book and find out how to find the adjoint of a 3 cross 2 and 2 cross 2 or 4 cross 2, 4 cross 4 matrix. Okay. Anyhow, I'll just tell it for a first term. Okay, so the first term is the cofactor of S plus 2. So this is the first term. S plus 2 is the first term. So the adjoint matrix will be a transpose of the cofactor matrix. So the cofactor of S plus 2 is this. That is S plus 3 into S plus 5 minus 4 into minus 1. So if you multiply that and simplify, you will get this S square plus 8S plus 19. Okay. And adjoint of this, sorry, the cofactor of minus 1 is minus of the first column and 0, 3 minus 1 S plus 2. Okay, so and you'll have a negative sign, but when you take the transpose, it will go here. Okay, anyhow, just refer some basic mathematics book to learn how to find out the adjoint of a matrix. Okay, so anyhow, I got the adjoint of this matrix like this. Okay, so the next thing is to find out the determinant of Si minus A. So Si minus A is already here. How will you find out the determinant? You can expand this matrix by either the first row or the first column. Choose any row or a column. Better choose a row or column, which has more number of zeros. So you can make use of the first row, okay, and you can expand this. If you expand this, this is what you will get: x cube plus 10s square plus 35s plus 41. Okay, so this is what is the determinant of this matrix. Okay, so I got uh, the system model, state space model. From the state space model, I segregated the matrices, and I found that I need to find out Si minus A inverse. For that, first thing I need to do is I should find Si minus A. I got it, and then I know that Si minus A inverse is an adjoint of Si minus A and determinant of Si minus A. I got the adjoint of Si minus A, also the determinant of Si minus A. Okay, so what next? I can substitute this Si minus A inverse by adjoint of Si minus A, okay, and this divided by determinant of Si minus A. So since determinant is a scalar quantity, I can take that outside, and these are all matrices. Now the job is just to put all these matrices here. Okay, so 1 by determinant of Si minus A, determinant of Si minus A, 1 by determinant of Si minus A, I put it here. And the next term is C. C matrix is available there. Okay, then the next is adjoint of Si minus A. We found it already. We found it. So that is also written. And then it is the B matrix. B matrix is also written here. Okay, B matrix. This is what is a B matrix. So if I multiply these three matrices, you will get S plus 2. See what is the size of this matrix? This is 1 cross 3, 3 cross 3, and 3 cross 1. So the resultant matrix is going to be having a size of 1 cross 1, and that matrix, that will be S plus 2. You may wonder, this is a very big matrix multiplication. It is very simple. So if I multiply this C matrix with this matrix, adjoint matrix, I'll get a row vector. Sorry, I'll get a row vector, because 0 into 0, 0 into this will be 0, 1 into this will be minus 3, and 0 into 0, 0 into this will be 0. So the first term will be minus 3. And similarly, if you multiply this, the second column, you will get only S square plus 7S plus 10, and the third element will be S plus 2. So if you multiply these two, you will get this row. Okay, now I have to multiply this row with this column. So obviously this into this is 0, this into this is 0. The only element that will remain is S plus 2. So ultimately this entire multiplication, that is the multiplication of these three matrices, will result into S plus 2. Okay, so therefore the answer, otherwise the transfer function for this system, okay, this state space model, is nothing but this S plus 2 divided by S cube plus 10s square plus 35s plus 41. Please note that the characteristic polynomial is nothing but determinant of Si minus A, which was explained in the previous lecture. Okay, so that is how we find the transfer function of an SISO system. Now we will take an MIMO system. Okay, So this is an MIMO system because you got two inputs U1 and U2 and two outputs Y1 and Y2. So obviously this is a two input, two output system, or I can call, in general, I can call this as an MIMO system. Okay, so for this system, let us see how to find out the transfer function or the transfer matrix. So again, we'll segregate the matrices here, A, B, C, and D. This is A matrix, this is B matrix, this is C matrix, and this is my D matrix. Here also D matrix is a null matrix. Okay, so since this has got two inputs and two outputs, obviously the size of this transfer matrix is going to be 2 cross 2. Okay, so again I have just written the expression. So what we need to find first is Si minus A as usual. Si minus A is S into identity matrix. Since the size of the matrix A is 2 cross 2, I'm also taking a identity matrix of the size 2 cross 2. So S into identity matrix minus A, Si minus A. So I get this. So now, as usual, the inverse is nothing but the adjoint of Si minus A divided by the determinant of this. So adjoint of this is found here, adjoint of this matrix. So just refer some mathematics book to find out how to know how to find out the adjoint of a matrix. And now I find the determinant of the matrix also. Okay. So both are formed. So for the given system with these matrices, we found the adjoint matrix, adjoint of Si minus A as well as the determinant of Si minus A. So this is what is the expression. Directly put all this 1 by determinant of Si minus A. Si minus A is this into C. C matrix is this. C matrix is this into adjoint matrix. Adjoint matrix is this, that is put, and B matrix is already there. I put this matrix here. So if I multiply all these matrices, three matrices, I will get a 2 cross 2 matrix because 2 cross 2, 2 cross 2, 2 cross 2. So all matrices are 2 cross 2 matrix. Therefore, the result also will be a 2 cross 2 matrix. And this is what you will get if you multiply. Okay. And now this is what. So you can see this is 1 by S square plus 4S plus 25 is common for all elements. So I can take this to inside this matrix, and all these elements will have a denominator of S square plus 4S plus 25. Okay. So this is what is G of S, and I got a transfer matrix instead of a transfer function. So we know that G of S relates Y of S and U of S in this way, and Y of S is Y1, Y2 because I got the two outputs, and U of S is U1, U2 because I got the two inputs, and this is the transfer matrix. So this is G11. So G11 is this, G12 is this, and G21 is this, and G22 is this. Okay, we already knew that. First element G11 is Y1 by U1. Y1 by U1 of S is this. Okay, and G12 is Y1 by U2. So this is what. So these are the separate transfer functions. This is a transfer matrix. A transfer matrix contains the transfer functions as the elements. The transfer functions, this transfer function relates Y1 and U1. This transfer function relates the Y1 and U2. And similarly, this one relates Y2, U1. Y2, U1 is nothing but G21, this one. G21. Okay, and similarly G22 is Y2 by U. So this is what. So I got all the transfer matrices. Okay, all the transfer functions as an elements of the transfer matrix. So in this first two examples, we understood how to get the transfer function of an SISO system and an MIMO system. Now we are moving on to the third example. This third example illustrates that the eigenvalues of the state matrix are the poles of the transfer function model, okay, or the transfer function poles of the system. So I'm taking a dynamic system, an LTI system's differential equation. Obviously, this is a third order equation. Okay, so the third order equation. And what I'm going to do is I will get the transfer function model of this system and get the poles of the system from the characteristic polynomial. And also I will get the state space model of the system, and then I will get the state matrix, and from that matrix I will get the eigenvalues of the system, and we will see that the eigenvalues obtained from the state matrix and the poles obtained from the characteristic equation of the transfer function model will be the same. Okay, so that is what is going to be illustrated through this example 3. So first let us get the transfer function model. To get the transfer function, what should you do? You should take the Laplace transform on both sides of this equation. So this is a third order derivative, so you'll get x cube y of s 6 x square y of s, because it's a second order derivative. Then the first order derivative term s into y of s, and y of t will have a Laplace transform as y of s, u of t as u of s. So now I can separate y of s outside. Now I can write this y of s by u of s is equal to 1 by s cube plus x squared plus 11s plus 6. So I got the transfer function model for the system. So this is a third order differential equation, and I got a third order characteristic polynomial here. So the characteristic equation is the characteristic polynomial, which is nothing but the denominator of the transfer function equated to 0. Now the poles of the system are nothing but the roots of the characteristic equation. So this roots you can straight away find from your calculator. You can use your calculator to find, because it's a third order equation. You can use your calculator to find out the roots of the equation, and you will see that the roots of this equation are -1, -2, and -3. So what we have done is, for this differential equation we got the transfer function model and we got the roots of the characteristic equation, or nothing but the poles of the system. Okay, now what we are going to do is we are going to move on to the state space model. So for the state space model, the first thing is to identify the state variables. So the problem here is we don't know how to take the state variables. Otherwise, if I give an electrical system, immediately you can take the inductor current and the capacitor voltages as the state variables. Or if I give you a mechanical system, you will take the displacements as one state variable and all the velocities as the another set of variables, state variables. But here there is no clue, there is no such clue, because we do not know what system is represented by this differential equation. So we don't have any clue. So in this cases, how we can take the state variable is, how we can choose the state variable is, see which variables change with respect to time. Okay, so So if you look at this equation, there is a differential term dy by dt. That means y of t is going to vary with respect to time. So therefore y of t can be a state variable. It is going to, since it is going to vary with respect to time, y of t I can take it as a variable. And if you look at this differential term d square y by dt, I can write it as d by dt of dy by dt. Okay, that means this dy dt is also going to vary with respect to time. Okay, so therefore dy by dt is another state variable. And let us look at this differential term. This is nothing but d by dt of d square y by dt. So which conveys a message that d square y by dt square is also a variable which varies with respect to time, and therefore that also can be taken as a state variable. So therefore the state variable we can take are y of t, dy by dt and d square y by dt. So these are going to be my state variables. So y of t is my first state variable and dy by dt is my second variable. Since y of t is already defined as x1, this is nothing but x1 dot. Okay, and the third variable is d square y by dt square, that I define as the third state variable. And d square y by dt square is nothing but d by dt of dy by dt. dy by dt is already defined as x2 and this is the first derivative of x2, so I can represent that as x2 dot. So I have defined all the state variables here. So this is how you should define the state variables if you are given a differential equation or a set of differential equations. Just look at which are the terms that vary with respect to time, and those variables you can take as the state variables. Okay, right. So having identified the state variables, we should get the state equations. So what we want is the state variables are x1, x2 and x3. So the state equations what we need are x1 dot, x2 dot and x3 dot. The equations for x1 dot and x2 dot are already available to us. x1 dot is equal to x2 and x2 dot is equal to x3. So only equation we need is x3 dot or dx3 by dt. So that we can get from the differential equation. Just rewrite this differential equation in terms of the state variables. So dq by d cube y by dt cube is nothing but d by dt of d square y by dt. D square y by dt is x3, so it is nothing but dx3 by dt. Okay, so and d square y by dt square already we have defined as x3, so straight away I can put it as x3. So dy by dt is x2 and y of t is x1. So that. So in this equation I got only x3 dx3 by dt as the derivative term. So all other terms I can take it to the other side. Now I got x3 dot also. So x1 dot is available here, x2 dot is available here. Now I got x3 dot also. So I can write the state equations. X1 dot is equal to x2, x2 dot is equal to x3 and x3 dot is equal to minus x1 minus 6x1 minus 11x2 minus 6x3 plus u of t. Okay, so these three equations I can write it in a matrix form. This is going to be the state equation, x1 dot x2 dot x3 dot as a vector, and then the first equation x2, it is having only x2 terms, therefore 0 1 0, and the second term is 0 for x1 and x3, sorry, x1 and x2, so 0 0, and it has only x3 term. The third term has x1 x2 and x3 terms, so minus coefficients are minus 6 minus 11 and minus 6. And only the third equation has got an u of t term. So put 0, 0, 1 u of t. So I got the state equation in matrix form. So in this matrix A or the state matrix A is this one. So I got the state matrix also. Now let me find out the eigenvalues of this state matrix. Eigenvalues of the state matrix are defined as lambda I minus A. Determinant of lambda I minus A is equal to 0. If I take this and if I equate it to 0, if I find out the roots of this, then I get the eigenvalues. Okay. So this is what is lambda I minus A. We can get this as the lambda I minus A, and its determinant. This is what is the determinant calculated for this lambda I minus A, and get you will get a polynomial in lambda. Obviously uh, this is a third order matrix, okay, and therefore you will have a third order polynomial. Okay, so to get the eigenvalue you have to equate that to 0. You have to equate that to 0. This has to be equated to 0. If you equate it to 0, you can again very well get the values as this. Please see this equation and this equation. Only thing is s is replaced by lambda here. And obviously this equation and this equation should give you the same roots. So hereby we understand that the eigenvalues of the state matrix A and the roots of the uh, roots of the characteristic equation in the transfer function model are one and the same. Okay, so uh, what we learned in this lecture, we obtained the transfer function of an SISO system. We obtained the transfer matrix of an MIMO system. So I think one more point I may have to explain in this uh, MIMO system, that is, if you look at this transfer functions inside this transfer matrix, all the denominators are the same. They are nothing but this determinant of Si minus A. So this is going to be the characteristic polynomial. So the characteristic polynomial is going to be the same irrespective of the input and output. So if you change the input and the output, what changes is only the numerator. That is one point to note. And the other point to note is we derived this from a system with two state variables. Okay, so this is the model. This is the model. So obviously you are able to see that this is a system defined by a two state variables. So for a two state variable system, we got a transfer function or a transfer function with second order characteristic polynomial, or this system, all these transfer functions are second order transfer functions. So you should understand that the order of the system is nothing but the number of states. Otherwise, a second order system will have two state variables, and a third order system will have three state variables. A fourth order system will have four state variables. Okay, so that is clear in this example also. In example 3, we took a third order system, and of course that resulted in a third order state matrix, or the system had three state variables. Okay, so that is an important observation we should make. And also we illustrated that the eigenvalues of the state matrix are nothing but the poles of the system. Okay, and while doing these three numerical problems, we also learned how to get a state space model if only the differential equation is given to you and you do not have any knowledge about the system. In that case, how you should get the how you should get the state space model for such systems. Okay, so these are the things we learned in this lecture. So I'll just recap of whatever we learned so far. In the first four lectures, we modeled the electrical and mechanical systems in state space. And in the fifth lecture, we understood how we can transform the state space model to a transfer function model. Okay, that was well explained in lecture 6 using from some numerical problems. The numerical problems covered both SISO, single input, single output system, as well as MIMO, multiple input and multiple output system. And certain other observations also we understood, like eigenvalues of a state matrix or the poles of the system. And also we learned to get the state space model only if the differential equation is available. So that is how we finish the lecture 6. And in the next lectures, we will see how a transfer function model can be transformed to a state space model. Thank you.